And welcome back. In this video, we're going to start looking at our continuous probability distributions. All right. And so there'll be a lot of parallels between what we do here and what we did in the last section. So let's start out with a definition here. F of x is a probability density function. So in the continuous case, we have a probability density function. This is the analog of a PMF in the discrete case, but in continuous, we say it's probability density, or abbreviated PDF. So, little f of x is a probability density function for the continuous random variable, CTS for continuous, the continuous random variable, capital X, defined over the set of real numbers. Defined over the set of real numbers if we have three conditions here. 1, f of x is greater than or equal to 0. Right? It's a probability density function. We should have non-negative results here. F of x is greater than or equal to 0. This would be for all x, where x is an element or a member of the real number system. In case you haven't seen that yet, this means is, oh, that's not the right pen that I want here. This fancy backwards E is an element of or a member of, and then this right here would be the real numbers. The real numbers. That's sort of the same thing over the set of all real numbers, right? That's the set of all real numbers. So 1, we have that. 2. The probability then that x takes on values between a and b is computed as follows. That is the integral from a to b of little f of x dx. In 3, the integral then from minus infinity to infinity of f of x dx should equal 1. Should equal 1, right? In this case, we're adding up essentially all of the possible probabilities, and so that should be equal to 1. All right. So something that's a little bit different in the continuous case than the discrete case, a key characteristic here to be aware of. Let me change my pen color here. Key characteristic to be aware of is that a continuous random variable has probability of 0. Has a probability of 0 of assuming exactly any one specific value. Assuming exactly any one specific value. Any one specific value. Okay. And that's for a couple reasons, and we can talk about that in a moment. One of the easiest actually ways to sort of see that here is if we take a look at what we have with this definition, and we look at this in a graphical sense. In the continuous case, graphing your PDFs, I'm just going to make an arbitrary curve here, right? Let's just say it's, something like this. Maybe is my PDF, right? Graphically, then the probability would be the area under the curve. And so let's say we wanted, here's A, right? Well, what we know is that the integral from A to A of any function, f of x dx, right, is equal to 0, right? There is 0 area under that curve. Is equal to 0. There's 0 area under that curve. 0 area under that curve, right? Integral from A to A, right? There's no area here, right? You think about some examples of continuous distributions. This is a little more hand wavy, but just maybe put an application to it, right? What is the probability that it rains exactly 3 inches today? Well, the probability that it rains exactly 3 inches today should converge to 0, because how do you know that it's exactly 3 inches? What if it's 3.000001, right? What if it's 2.999999? That's not exactly 3, right? You can't get exactly 3 inches, right? But we can come up with a range. So, well, how likely is it to get from 3 to 4 inches, right? And in that case, that may be something like from A to B, for example. And then you're computing the area under the curve, which is just an integral problem. And you're going to get this highlighted area is what you're gunning for at that point. So when we're doing probability questions from a continuous distribution, we are then looking at areas under curves, and our calculus skills really need to come into play. So here's where that prerequisite in this class of having integral calculus comes into play. We need to do some integrals in order to answer these types of probability questions. Let's go back here. Example. Suppose that little f of x is equal to, we'll say x squared over 3, from -1 to 2. And then it is implied in the fact that this is a PDF, but we'll say 0 elsewhere just to be specific. Just to be specific, 0 elsewhere. Okay, so here's what we'll do. Part A. First, verify f of x is a valid density function. Verify f of x is a valid density function, okay? Well, take a look at this. Let's take a look at this. So first, for verify it's a valid density function, we can look at these 3 conditions. Let's look at f of x being greater than or equal to 0 for all x when x is any real number. Is it greater than or equal to 0? Well, certainly it's greater than or equal to 0 when you're outside of the -1 to 2, because this is equal to 0 everywhere else, right? So we know it's at least 0 there. What's of interest is maybe between -1 to 2, because there's some variance, right? This is now x squared over 3. So what do we know about x squared over 3? Well, x squared is greater than or equal to 0 for all x. For all x. And specifically, when x is from -1 to 2, right? You square a negative number, you're going to get a positive. You square 0, you get 0. You square positive, you get positive. So that's greater than that. Dividing by 3 is not going to change the sign of it being positive or negative. Then dividing by 3 will not change it. So x squared over 3 is greater than or equal to 0 for all x as well. For all x as well, okay? And certainly it's 0 elsewhere, right? F of x is 0 elsewhere, so we are good to go. We are good to go. 1 is satisfied. So condition 1 is satisfied. Condition 1 is satisfied, all right? What else do we need to do then, right? We really need to verify condition 3, because 2 is basically just saying how you compute the probability. Condition 3 is saying, in order for this to be a valid PDF, and if you integrate over the whole real number line, that is the whole possible sample space, right? The sample space on a continuous distribution is all real numbers, something that's equivalent to the set of real numbers. So the sample space here, when we integrate over everything, we better get 1, because that's adding up all the probabilities. So let's verify that we get 1 when we are integrating. So we'll verify 3. To verify 3, we compute the improper integral from -infinity to infinity, x squared over 3 dx. Does that look right? -infinity to infinity, f of x dx. and we need to compute this and check, is this equal to 1? Does this equal 1? Is the question. All right. So let's go ahead and take a look at doing the integral here. And we'll go ahead and set this up. Integrate. Now I'll do the actual integral calculation here. X squared over 3 dx. Okay. Now, one thing we get to do with this, here is, while this looks like an improper integral, we don't need to really worry about too much because, again, this PDF only takes on the value x squared over 3, when we're between minus 1 and 2. It is 0 everywhere else. Right? So this is basically 0 plus the integral from minus 1 to 2 of x squared over 3 dx plus 0. Right? And again, why are these zeros here? We don't really need to write these, but where are these 0 coming from? This 0 on the left would be all the values to the left of -1 on your number line, and this 0 on the right would be all the values that are greater than 2 on your number line, right? So we really just need to compute the integral from minus 1 to 2. What is the antiderivative here? What's the antiderivative of x squared over 3? Well, increase your exponent by 1, and then you divide. So that'd be over 3 times 3. Evaluate from minus 1 to 2. So this is x cubed over 9 evaluated from minus 1 to 2. X cubed over 9. All right. We're going to go ahead and plug in 2. 2 cubed over 9. Minus the evaluation at -1, which would be -1 cubed over 9. And let's see what we got here. 2 cubed is 8. So we have 8/9. Minus -1 cubed. Minus a -1 cubed. -1 cubed is -1. So that's minus -1 over 9. So 8/9 minus a -1, that becomes plus. 8/9 plus a 9th is, in fact, 9 over 9, which is equal to 1. Sort of what we were expecting. So we did verify 3. Good to go. The probability is equal to 1. We have a valid PDF. Verify fx is a valid density function. Looks good. All right. I'm going to ask a part B to this problem. Now that we've checked that it's a valid probability density function, let's just utilize it. Typical question you'll get will be, find the probability then that x is between some values. Say 0 to 1 in this case. Let's say x is between 0 to 1. All right. Well, according to the definition above, this should be equal to the integral from 0 to 1 of f of x dx, right? 0 to 1 of f of x dx. Right? A to b. According to this definition, x goes from a to b. Integrate a to b f of x dx, right? Okay. Then what do we have here? So this is the integral. Now, what is our PDF on the interval from 0 to 1 as we go from 0 to 1? 0 to 1 is right in this range here, right? Includes 0 to 1. This includes 0 to 1. That says includes. Includes 0 to 1, so we're going to use the x squared over 3. So we can use the x squared over 3 dx. And let's see what we get. Antiderivative should be the same here. X cubed over 9, but now we just evaluate this from 0 to 1. So that's going to be 1 cubed over 9 minus 0 cubed over 9, which is just 0. And so that probability then is 1/9. 1/9. All right. Let's try one more. One more example here. Let's determine the value of C needed so that the following is a valid PDF. So the following is a valid PDF. And actually, we might get this type of question in the discrete case too, but instead of integrating, we would just add things up, right? But let's try this for this question. So what's the PDF potential? F of x is C over x plus 1 cubed for x greater than or equal to 0, and then it's 0 otherwise. 0 otherwise. Determine the value of C so the following is a valid PDF. All right. How do we pick out our C value here? Well, what we know, in order for this to be a valid PDF, we must have the integral from minus infinity to infinity of f of x dx equaling 1, right? That has to equal 1 in order for this to be a valid PDF. Okay, so how do we utilize that? Well, that means then that should imply that if we integrate from, in this case, x is greater than or equal to 0, if we integrate from 0 to infinity, c over x plus 1 cubed dx, if we integrate over that range, this has to equal 1, right? That would have to equal 1. So what we can do is we can do this integral, get the antiderivative, and set up an equation. We can set up an equation. So what is the integral from 0 to infinity of c over x plus 1 cubed dx? Let's go ahead and work this antiderivative. If you're struggling with this integral, you could do a couple things. C is a constant, so we can factor that constant out in front of the integral via the constant multiple rule. So we're going to integrate c times the integral. And then 1 over x plus 1 cubed can also just be written as x plus 1 to the negative 3. And that'll probably make the integral a little bit easier. You could do a u substitution here if you need to for x plus 1, or if you're comfortable with the integration at this step, that is fine by me too. We have c times. You have the power rule here, which means you need to increase your exponent by 1, and then you divide by your new exponent. This is going to be evaluated from 0 to infinity. Evaluated from 0 to infinity. And so let's clean this up a little bit. We've done the calculus, or the antiderivative. So let's make this a little bit easier to evaluate. We have negative c over 2 times x plus 1 to the minus 2 power. Let's see here. X plus 1 to the negative 2. Evaluate that from 0 to infinity. All right, and then I don't like punching things into the negative 2. I'd rather actually go back and rewrite this as just 1 over x plus 1, the quantity squared, evaluated from 0 to infinity. So I'm going to move that back to the denominator by negating the exponent again. There we go. That looks good. And let's go ahead and plug these things in. Now, technically here, as we evaluate this at infinity, we're doing an improper integral. We're doing an improper integral, and so we should be taking a limit if we want to be formally correct. But at this stage in your calculus skills, we've hopefully learned that and have a good handle on what we're doing. That infinity is not an actual number, but in terms of getting the answer here, we're going to kind of wave our hands a little bit here and say, well, what is this? What happens when you plug in infinity here? If I plug in infinity, I'm getting 1 over, let's say, infinity plus 1 quantity squared, minus the evaluation at 0 is 1 over 0 plus 1, the quantity squared. All right, and we look at this and we say, well, what is 1 over infinity plus 1 squared? Well, infinity squared is just something really large. You have an extremely arbitrarily large number in the denominator. This first term then is essentially 1 over infinity, which we know trends to 0. 1 divided by an extremely large number trends to 0. So we know this term is going to 0 out. That term is going to 0 out. So we have negative c over 2 times 0 minus 1 over 1 squared. So there's a negative 1. So what do we have? Negative c over 2 times a negative 1. The double negatives cancel there, and we get c over 2. Okay, we've done the integral. So what do we need? Remember, we need this to equal 1. That has to equal 1, right? We need c over 2 to equal 1. So c over 2 has to equal 1. In order for this to be a valid PDF, that means c then, solve for c has to equal 2. C would have to equal 2. So in order for this to be a valid PDF, c needs to be 2. Okay, and that is in fact the correct answer. All right. Cool. Once we know that, then you could do other questions, right? You could ask a follow-up. You could do, a probability question like this. Find the probability x is between 0 and 1 or whatever, and you can just use this value that c is equal to 2, right? So in this case, we could say f of x is equal to 2 over x plus 1 cubed for x greater than or equal to 0, and 0 otherwise. 0 otherwise. There we go. All right, I'm going to go ahead and leave it at that for this video. We'll pause here. Let's take a quick bathroom break, quick drink break. And when we come back, much like we did in the last section, we will take a look then at the CDF, the cumulative distribution function. This is a bit more interesting, a little bit more complicated when we're talking about the continuous case. So we'll save that for the next video.